Welcome. Today we will discuss the prediction error method and the maximum likelihood estimator. The prediction error method builds on the principle that we are using a prediction of the future signal. So I assume that I have a way of predicting y of t at the next time instance. So I assume that I have data up to y of t, that is I have a vector y1 up to yt, and then I'm trying to predict the value at y of t plus 1. And this I do using the unknown parameters here. So you see that my capital theta consists of both my unknown parameters as well as my data. So we will in the continuation look at how this shall be done, but for the moment let's assume that it can be done. And with this we will then do our best. We will predict what the future value is and compare it to the actual value. And the error we make is going to be my prediction error, epsilon of t plus 1, like this. So what I wish to do now is I wish to form my estimate of theta such that I make this as small as possible. I wish to find a method that minimizes the prediction error method. The prediction error, I'm sorry. So what I do here is that I will search, I will formulate the error for a given candidate, parameter candidate, so that is for my particular parameters that I'm trying. I will form the prediction, then I will form the prediction error, and then I will sum up this error and see if I can find the parameters that give me the smallest possible errors over all possible parameters. So basically this is turning into a multidimensional minimization. So say that I have an ARMA PQ, that means that I will have P plus Q parameters in theta. So this is going to be P plus Q dimensional minimization, so that for each point in this P plus Q dimensions I will have a given new parameter value, and I will try out all the possible parameter values possible. For each one of them I will predict the future and construct the prediction error, sum it all up over all time that is available, and then I will compare this for all the different parameter sets and pick my theta such that it is the one that minimizes this prediction error. Notice that my sum here is just over t. This sum will depend on my model. So I'm summing over all available prediction errors, and say for instance that I have an ARMA or an AR. These will depend on previous values of the process. So I will have y of t minus 1, t minus 2, and so forth. And so therefore my time will be limited. It will not start at 1 or 0. It will typically start at p. So the first possible value I can have is p. But this depends on the model. So what I do is I will form this prediction error, sum it all up, and find the parameter vectors that is the one that minimizes this. So let's look at an example. So I have an ARMA PQ. That will be the noise part, which is the MA part, and then I have the AR part, which is then the alpha. So I will gather this up as a linear model. Notice that in my linear model, my regressor will contain the noises like this. These are of course unknown. My parameter vectors theta are here also unknown, so they are my P plus Q parameters that I wish to minimize over. But I have to deal with the fact that I don't know my noises. So what you typically do is that you assume that the prediction error is a reasonable model for this. So what that means is that when I form my prediction error, I will form it as y of t minus y of hat of t given t minus 1, and I will call this the epsilon of t, as I mentioned before. I will pick this epsilon of t given t minus 1 as an estimate of these errors that I have here. So I will form it as my previous prediction errors, and I'll put them in here, and then I will find the minimum. So if my model is correct, these errors will be pretty close, given that my prediction will be pretty close. So to say that again, so if my model, my theta is correct, that means that my prediction y hat of t is going to be pretty good. So it's going to be close to the true one, which means that this error that I get here will be essentially the same as the additive noise process E of t, which is just what I want. However, if I have another parameter vector, obviously my estimate, my prediction will not be very good. Therefore, my error will be bad. So that means that when I sum up the squared error, this will be something really bad. So this will also cause my cost function, the sum of my epsilon of t, to have what we call a multimodal shape. That means that if I plot it in one dimensions, it means that for the correct value it will have a minimum, but for any other parameter values it will have many local minimas like this. So it's very difficult to optimize it. So I will have a minimum at the correct location of this cost function. Of course, this is going to be p plus q dimensional cost function, but I will have many, many local minima. So it's really important that I have a good initial estimate when I form it. Since it will depend on earlier noise models, I have to make my estimate recursively. This is going to be my prediction of y of t. So this is equal to y of t plus 1 given t. This is my conditional expectation, as we saw in the first part of the book. And I will then build that, as I mentioned, using my prediction errors. So in order to be able to do this, I need to form these prediction errors recursively like this. That also means that I have to have some initial values that I need to start from. So I cannot predict my first y of t, where t is equal to 1 up to p. I cannot predict those because I don't have any data that can go back in time like that. So typically I need to set my prediction errors to 0 to be able to deal with that. So that will of course be an approximation. It also means that my sum will have to start my sum over my prediction errors. Instead of it will start at p, as I mentioned before. So I cannot start at time equal to 1. And so I will, as I noted before, I will have a multimodal and multidimensional minimization. So this is going to be really critical that I find a good initial value. But if I do, I am able to get a very accurate estimate of these parameters. Should I have a model which does not depend on unknown noises, like for instance if I have an AR, then this will coincide with the least squares estimates as shown in the book. So this is then going to give me the same estimate. But if I have an ARMA process where my regressors depend on my data, I will get an estimator that is better than the least squares, because least squares cannot handle that. Okay. In MATLAB, there is a command PEM that you can use to compute this, and I'm sure there's in R and so forth. And typically you should remember then that the initial estimate is quite crucial. So if you get a poor estimate using PEM, it might be the easiest thing might just be to give it a slightly different initial estimate so that you avoid this local minimum that you got caught in. We move over to the maximum likelihood estimator. The maximum likelihood estimator builds on the fact that you assume that you know the probability density function of the data. And in our case, since we assume it to be Gaussian, what we try to do is we try to find the parameters theta such that we maximize the probability density function. So if I plot the probability density function, it's going to have its maximum around the mean, which will be then the location of the parameters. So what I try to do is I try to find my unknown parameter vector such that I maximize the probability density function, the likelihood. And since I have many samples, I have n observations, I need to look at the multidimensional Gaussian distribution, which looks like this. And you notice that it will depend on the covariance matrix of the noise, which is of course unknown, and which is going to cause us problems. And then it also depends on my unknown parameters that I seek. And again, if I have something like an ARMA model, I will have my noise coefficients here in the regressor, which will then of course again cause me problems. So what I wish to do is I wish to find my theta such that I maximize the likelihood. So fortunately what I can do is I can use the fact that the log is a monotone function. So the argument that maximizes theta is the same argument that maximizes the log of the likelihood function. And the log has this nice property. I will get away with having remove the exponential function. So if I take the log of it, I will get the term here, which does not depend on theta. I will have a term that depends on my covariance matrix, which is unknown, and then I will have a term that depends on theta. So that means that my maximum likelihood estimator is going to be the maximum of these negative functions. So what I typically do is I multiply by -2. So now it's a minimization, and I got rid of the 2. So you see here I have my maximum likelihood estimate as the minimum over the log determinant of the covariance matrix plus this extra term. To be able to solve this, I do need to have some kind of assumptions on the covariance matrix. And here I typically make the assumption that the noise covariance matrix is known. Clearly this is not realistic, but we will have to make that assumption for now. There are ways to deal with this, but we will come back to this at a later point. If Re is known, however, then this log determinant does not depend on theta either, just as in the constant term. And of course, then it will not affect the minimization, so I can just remove it. And then my maximum likelihood falls down to this condition. And here you should see that this is nothing but the weighted least squares. This is the formulation we used for weighted least squares. For an ARMA model, I will have that the covariance matrix, the unknown covariance, just depends on the noise power. So I can rewrite it such that I will actually have my noise power as one of the unknowns in my model. I don't have to make the assumption that my covariance matrix is known. Rather, I will include the minimization over the unknown parameters and the noise power, which then will be my unknown. So the way to deal with this is I will take the differentiate this function with respect to the noise power, and then I will get just this, and then I will insert this value into this equation wherever it says sigma square, and I will get this form here, which if you look at it, you'll see that this is just the same form of expression as the PEM estimator. So that means that my estimator for my maximum likelihood estimator is the same as my PEM estimator if I have an ARMA process. That also means that you can use the PEM command in MATLAB to estimate the maximum likelihood estimate, or rather the same, the PEM estimate in this case. One thing to notice here is that the maximum likelihood estimator is going to be the estimator, since it's maximizing the likelihood function, it's going to be the estimator that is giving you the best possible performance. In the general case, it will give you a variance which is the lowest possible variance of any unbiased estimator. So it will reach what we call the Cramer lower bound. It's so-called statistically efficient. That also means that for any reasonable amount of data, there is not going to be any estimator that gives you a better estimate than the maximum likelihood estimate. However, as in this case where the ML and the PEM are coinciding, the ML estimate in general for a typical process is very hard to actually form. It will be multimodal and multidimensional, so in many practical applications it's going to be very difficult to actually estimate it. Even though we know that it's going to be the best thing, it might not actually be feasible to do. So that's good to keep in mind.